Hi everyone, welcome to another video. Today we are going to talk about caching, and this is a method to boost performance of scaling the distributed systems. So let's get started. So before talking about different aspects of caching, we need to first understand what it is. So what is caching? It is storing frequently accessed data closer to the user or application for faster retrieval. So the key important bits are the frequently accessed data and faster retrieval. And that's all caching is. It makes sure that whichever data we need to read or write or need to process on again and again, we store that data in some high performance storage so that we can retrieve it more easily, and the performance is faster and user experience is better when they use our distributed systems. So why caching? Performance drastically reduces data retrieval latency. This is the main reason always for caching. And then reduce load, of course, takes trace of backend databases and services. Of course, for example, you have a very big collection in MongoDB or some other database of your choice. If you don't cache, all your requests will hit database, and that is not really good for a large database, especially if it has a lot of documents. And also the queries can be slower. So instead, you need to cache some data, frequently accessed data, in memory so that it can be retrieved faster. That is just one example of a use case. Then scalability. It allows systems to handle more requests efficiently. Because on caching, we focus on the performance improvement. Even though the database size increases, we are not too bothered about the performance of the database. We have effective caching strategies. Of course, we need to be bothered about database performance as well, but the sole dependency on the database is reduced. And then cost savings. Sometimes less resource consumption for repeated data access, especially if reading operation on your database is expensive. Generally with our cloud providers, we are charged per read for databases. So if that operation is expensive, you can imagine caching can be cheaper, may turn out cheaper, although caching requires faster storage, like generally in memory, and generally having a lot of memory, maintaining a machine with a lot of memory can be expensive. But we need to find out the price, calculate the price, and it's always a balancing act. Let's briefly talk about where caching is implemented. So first, we briefly talk about the client-side caching. So for example, your web application, it is accessed by a browser. In that case, the browser-side caching, it makes sense, and it stores static assets like images, CSS, JS locally on user's device. So if you have seen that when you visit a website for the first time, the website might load slower, but on subsequent visits, the website resources, they load faster, and that is all due to browser-side caching. Then server-side caching. Well, we need to first, there are several levels where we can do the caching. First, let's talk about the application level, which is in memory. So whatever code we write, whatever services we deploy, in the memory of it, we can cache data directly within the application process. This is a very fast retrieval, but it is not shared across instances. Because it is stored in memory, of course it is fast, but if our services have quite a few instances and each of the instances maintain their own cache, then these caches are not shared, and there is not a way to coordinate between each of these cache instances. So how do I solve this problem? So there came distributed cache. So in distributed cache, we completely deploy the cache in a separate dedicated cluster, and Redis, Memcached, all these technologies are for that purpose. So in this case, there is a completely separate cluster for cache, and which would have a few servers of cache, and then it can be connected to our application layer. And these deployments, the application deployment and the cache deployment, can be maintained separately. And in this case, there is a coordination between each of those cache instances, for example, Redis and Memcached. And yeah, it can help us a lot in modern distributed systems. And then finally, let's talk about database caching. So internal database mechanisms for query results or data blocks. So almost every modern database supports it. For example, MongoDB, whereas the frequently queried items are cached in the database itself. Now let's talk about few common caching strategies that we implement in distributed systems. First, let's talk about lazy loading. So this is something where the app checks the cache first while reading, and if there is a cache miss, then it fetches from the DB or whichever data source it is that it needs to fetch data from, then stores it in cache. And while writing, the app directly writes to DB and then invalidates the corresponding cache entry. So pros, there is simple, the data is fresh on a miss, and the cons is initial latency for the first access. So let's imagine this is our client, and then we have a cache, and there is our server, and there is our DB. So whenever there is a write request, the write request directly goes to the DB, as the server can also invalidate the cache. And whenever there is a read request, the read will first go through the cache. Read first goes to the server, and then server checks the cache, and if the item is present in the cache, the server directly retrieves it and then returns it to the user. And if not, it will first load it from the DB and then store it in the cache, and then finally give it back to the user. So you can of course see, like, when we first try to load a data, then that retrieval can be slow because the cache is not populated yet, because this is lazy loading. For the first time, the cache does not have the entry, it only exists in the DB, and then server gets the entry from the DB, puts it in the cache, and then returns the response to the reader. Our next strategy is write through. So in write through strategy, an app writes to cache, and then the cache synchronously writes to database. So whenever there is a client and there is a server, this is a cache, this is a DB. So whenever we first write something, the server first writes to the cache. So this is 1, this is 2, and then the cache will synchronously write to the database. So here the cache itself is responsible for writing. And what are the pros there? The data consistency. The cache and DB will always be in sync. Of course, you can see every write goes to the server, then cache, then the DB. And the cons are slower writes due to synchronous DB call. Of course, the server is not just writing to the DB. First, it is updating the cache. That cache is then updating the DB, and everything is happening in the synchronous call. So the write can be slow, but in the advantage of data consistency. Next, let's talk about the write back strategy, where the app again writes to the cache, and the cache asynchronously writes to the database. So similarly, like before, the client, it first writes to the server, and then the server is accessing the DB and the cache. So it first makes a write request to the cache, and then after it gets the acknowledgement, it just tells the client, okay, the write has completed, and then later the cache asynchronously writes to the DB. So in this case, of course, you can see the writes are way faster, because generally the cache is a very fast storage, and the server just needs to take care of writing to the cache. It does not need to wait for the write to the DB. And the cons are potential data loss on cache crash if it is not already synced to DB. So let's say I have written something to the cache, but before the cache actually wrote the same data to the DB, the server or the cache crashes, and in that case, the data will be lost. And we can also briefly talk about the eviction policies. So here are the two most commonly used eviction policies. The first one is LRU, or least recently used, which is the most common policy, and it evicts the item used longest time ago when the cache is full. So let's quickly talk about it. Let's say I can store some items in the cache, and there are some items here, A, B, C, D, E, and always whichever item is accessed the most recently, that item will be put forward. So for example, if we now access C, then later the cache will look something like this. C will come first, then A, B, D, E. So in this case, of course, you can see the E is the least recently used, entry. So if there is some new entry that comes up, which is, let's say, F, so F right comes, so in this case E will be evicted. So F, C, A, B, D. Okay, and then we also can have a strategy based on time to live, where the data expires after a set duration, the cache is invalidated and the cache needs to be refreshed. Next, let's talk about caching pitfalls. What are the challenges or the complexities that can arise from using caches? Of course, the main concern is cache invalidation. We always need to make sure we do not read invalid or old data, stale data, while we are reading from cache. Of course, cache gives us the benefit of added performance, but it also means maintaining a copy of the same data. We have the source of truth, which is DB, but we also maintain the frequently accessed copy in the cache, and it defeats the purpose if the cache has invalid data. Even though the performance is good, the data can be invalid. So it can be okay in some cases, but generally it's not. So we need to ensure the cache data is not stale. So that's why a lot of the caching strategies that we discussed a while back, all of them invalidate the cache on the right, and that makes sure the cache data is always up to date. So when cache data does not reflect the most current state of the source of truth, of course this is the stale data. And then mitigation. How do we mitigate the issue? We can add a TTL so the cache data is expired automatically, explicit invalidation from the server side, and then event-driven updates. Then cache coherency or consistency. So what if we have a lot of copies of the cache, or like if the cache is replicated, how do we maintain that? So in that case, we need to maintain identical data across multiple cache instances, and this is especially challenging if we implement the cache in the application layer itself. But with distributed cache solutions, for example, Memcached and Redis, it is less of a problem if the cache cluster is managed correctly and independently. Then cache stampede or thundering herd problem. Let's say many concurrent requests miss the cache and they overwhelm the backend. As you can see, the cache is generally stored in memory, and memory is expensive, so cache will always have much less capacity generally compared to our storage solution. And if there are a lot of requests missed, then there will be a lot of new updates to the cache. There will be, first of all, a lot of read requests to the cache, but the reads are missed, so the application will visit the database first of all, and that will result in increasing load in the database. And then all those updated entries can be written in the cache at once, so the cache is very busy in that case. And we need to implement strategies in our distributed system so that the cache is not overwhelmed, and that we only can decide after we understand the data access pattern of our systems carefully. What are the mitigations of this cache stampede? Which is request coalescing, which is like it can be batching of many requests, then distributed logs, cheated TTL, etc. Then hotspots. When a few specific data items are disproportionately accessed, leading to contention. It can be something like a celebrity problem, whereas a hugely followed celebrity in systems like Instagram, their data is accessed much more compared to normal users. So in that case, normal caching strategy won't work, and for those celebrities we need to maintain cache separately, maybe a whole separate instance for a few celebrities together, and like grouping a lot of normal users together so that the request is distributed evenly across the caches. So of course you can understand caching is a complicated topic, and we need to cache wisely. So we can't cache everything because the memory is very expensive, the caching storage is generally expensive and built at a higher rate. So we need to identify critical, frequently accessed data, especially cache the slow to retrieve data. So if we have frequently accessed data that is slow to retrieve, it makes sense to cache that. Then start simple, of course, and scale as needed. Begin with basic caching, for example, application level, and if that does not serve your purpose, then move to distributed solutions like Memcached, Redis we talked about. Measure everything. So in distributed systems, the observability is very important, and using proper implementation of observability, we can monitor the cache. So monitor the cache hit ratio, miss ratio, eviction rates to understand effectiveness, and always be up for tuning your caching strategy based on the metrics you find. Plan for invalidation. It's crucial. How will you ensure that your cache data remains fresh? Yeah, reading stale data is a very complicated problem in cache and very crucial problem to solve. So always keep in mind you have the effective invalidation strategy. Consider the trade-offs. Caching adds complexity, balance performance gains against the operational overhead. Do you really need that much performance gain? If you don't, maybe don't go for caching anyway, because caching can be expensive and you are maintaining two sets of data. So whenever possible, just keep the system simple and take a decision on whether to cache or not. What are some of the popular tools? Redis, which is versatile, Memcached, which is used by Meta. So that's it for caching for now. Thanks for watching the video. If you like my video, please hit the like button and please share my content with others and subscribe to my channel. Thank you. See you in the next one.